looking at section 2.6, part 3. In the previous sections, we've looked at what happens when we have our horizontal asymptotes and our vertical asymptotes. There's a third type of asymptote that we're going to look at as well with our polynomial functions or our rational functions. We're going to look at what's called a slant asymptote. Now, if you think about slant, obviously it's not vertical or it's horizontal. It's some sort of diagonal looking asymptote. So it tells us that the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So it has to be exactly 1 more than is 1 more than. So the top is 1 greater than the bottom. So it says in general, if our function f of x is equal to p of x divided by q of x, p and q have no common factors, and the degree of p is 1 greater than the degree of q, we find the slant asymptotes by dividing q of x into p of x. So just like what we've looked at already previously in chapter 2 is using our division of polynomials. How do we use synthetic division or long division? So let's look at an example. It says to find the slant asymptote of f of x is equal to 2x squared minus 5x plus 7 divided by an x minus 2. So it states that the degree of the numerator, 2, is exactly 1 more than the degree of the denominator, 1. It says to find the equation of the slant asymptote, divide the numerator by the denominator. So we're going to use synthetic division. I think at this point it might be a little easier for some of us. We pull off our our coefficients, the leading coefficient or all of the coefficients. We have a 2, a negative 5, and a 7. And then we are dividing by this 2 on the bottom. So we take that first 2, drop that down. 2 times 2 gives us 4. Negative 5 with 4 gives us a negative 1. Negative 1 times 2 is a negative 2. And that's going to leave us with a remainder of 5. So we started with a second power polynomial. That means that that's going to leave us with 2x with a minus 1 and a remainder of 5. So we're left with a 2x minus 1 added with 5 compared to what we divided by. We divided by an x minus 2. So that is what we would get when we do that division. Now we're looking for a slant asymptote, and a slant looks like a diagonal, which means we're going to be kind of looking for a slope-intercept type of an equation. This piece right here is going to give us the equation of that slant asymptote. And we're not going to worry about the denominator. I'll explain that in a moment as to why we're not going to worry about the remainder. So if we were to take this information, we found that the equation of the slant asymptote is going to be this 2x minus 1. So we're going to have the equation 2x minus 1. So if you look at that graph, do you see where they have our slant asymptote of our 2x minus 1? That kind of has that red dashed line that you see there. Right, we have a y-intercept of negative 1. We have a slope of up 2 over 1, slope-intercept form, back to algebra 1 stuff, right? The other thing to look for is that vertical asymptote, and that's found by looking at your denominator. If you set that equal to 0, when x is equal to 2, that's going to cause problems. So we say we have a vertical asymptote at x is equal to 2. So once you have those two asymptotes drawn in there, then you can pick a point, plug it in, or pick a value of x, plug it in to kind of find out what that graph looks like if they're asking you to graph it, right? Okay, so let's look at why do we not care about that remainder. So it says observe that. They give us an example. This is just a screenshot from the textbook if you want to go back and read it for yourself. It says that f of x is equal to, and they took the polynomial expression, they did the division, they have what the slant asymptote is, right? That's our slope-intercept form. And then they have the remainder. And why do we not care about the remainder? This says down here that as the absolute value of x, whatever x is, positive or negative value, as it approaches infinity, the value of that little piece is going to be approximately 0. So if you think about that, if I were to have an x value of 10, right? 10 minus 1 would be 9. We'd have a fraction 2/9. But if that was a 100, 100 minus 1, that would be a 2/99. What if that was 1,000? That would be 2 out of 999. Do you see how that piece is getting smaller and smaller and smaller? So as that x value is going to approach infinity, some really crazy big number, right? That fraction is going to get very, 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 very small. So that's where it says that thus, when the absolute value of x is large, the function is very close to y is equal to x plus 1 plus 0. So that remainder is going to end up getting really close to 0, which is why we don't worry about it. If you want to read the rest, feel free to pause it and take a look, but I think you got the idea. All right. So the last thing it just said was that the equation of the slant asymptote is obtained by dropping the term with the remainder. So let's take a look at one more example, an application problem. It says that a company is planning to manufacture wheelchairs that are light, fast, and beautiful. The fixed monthly cost will be $500,000, and it will cost $400 to produce each radically innovative chair. Not just a regular wheelchair, but a radically innovative chair. So it tells us for the first part to write the cost function C of producing X wheelchairs. So the total costs are going to tell us to use the C is going to equal, well, let's go back and see what we have. It has a fixed monthly cost. We're paying $500,000 and it's going to cost $400 to produce each chair. So that means we have $500,000 added with 400 times the number of chairs. That gives us the cost, how much money we're putting out, $500,000 and $400 times each chair. Then it says to write the average cost function. And that's where that C bar comes in, of producing X wheelchairs. Well, if we're finding an average, in general, to find an average, you're going to add all the numbers together and divide by how many you had all together, right? Kind of like you add all the numbers up and divide by the number of numbers when you're finding an average or a mean cost. So what happens is we want to figure out what that total cost is and then divide it by the number of chairs that we're ending up making. Well, the total cost we already found with our cost function. So our C bar is going to equal, the total cost is going to be what we found up on this last one up there. That 500,000 plus the 400x. But now what we're going to do is we are going to take that and divide that by the number of chairs we have. That's going to tell us the cost it really is looking at per chair because we're factoring in that extra $500,000 cost. So we're going to use this to continue on with the next part. So they want us to find and interpret what happens when we have the C bar of 1,000. So what happens if we do 1,000 chairs? Well, a little repetitive. We're going to have this 500,000 plus the 400x divided by x. And what they want us to do is in place of x, we're plugging in 1,000. What if they do 1,000 chairs this month? How much is going to be the average cost of that chair? So if we were to take and plug in, we have our 500,000 plus 400 multiplied by 1,000 divided by 1,000. And you can take your handy dandy calculator and do some calculations, or I'm going to show you some shortcuts if you didn't know this. Because I'm dividing by 1,000, I'm dividing by a 1 with 3 zeros. If I were to cancel out 3 zeros from this, I can cancel out the 3 zeros from this, and I can cancel out 3 zeros from that. And guess what that leaves me with? A 500 added with 400 and dividing by 1. 500 plus 400 is going to give us 900. So in this case, the average cost per wheelchair of producing 1,000 wheelchairs per month is $900. Well, it's going to cost $500 just to make the wheelchair, but then there's an extra $500 per wheelchair to help us cover all those costs that we have within that company. What happens if, so that was 1,000 chairs, what happens if we do 10,000 chairs? So kind of using that same function, I'm going to just kind of squeeze them onto the same page. What happens if I have my $500,000 plus we have 400 that's going to multiply by 10,000. And we're going to divide that by 10,000. I'm going to do my little trick. I'm taking away 4 zeros and 4 zeros and 4 zeros. 1, 2, 3, 4. That leaves me with 50 plus 400. If you don't like my math, grab a calculator. 50 plus 400, how much is that going to cost now? That's going to be $450 on average per chair. What happens if I have 100,000? So again, let's plug that into our initial function that we have. So that means we have our 500,000 plus the 400 times, now we're doing 100,000 and dividing that by 100,000. And again, if you like my little trick, take out 5 zeros, take out 5 zeros, take out 5 zeros. We now have a 5 plus a 400, which is going to give us 405. So let's take a look at what we had, right? The first one that we had, right? We plugged in 1,000, we got 900. That's not so cost efficient, is it? We then plugged in what happens if we make 10,000 chairs in a month. We're at 450. That's a little better. So each chair is really only costing that extra like $50. But then when we went to 100,000, we're now at 405. What number do you think we're going to end up getting close to? We have 450 and then it only goes to 405. Let's take a look. It tells us to find the horizontal asymptote. That horizontal asymptote is going to tell us at what number are we getting really, really, really close to but never going to touch. If I were to find the horizontal asymptote of my function, right? If you remember our function was where we had that 500,000 plus 400x, and that was divided by x. Take a look at the powers of x. What are they? Well, they're the same, aren't they? So I have the same power, which means I have what is a horizontal asymptote? We're going to have a horizontal asymptote at 400 divided by 1, which is going to be 400. So what would we expect to happen? No matter how many chairs we keep adding in, it's never going to get below or even touch that 400 point. So it says, right, we had our horizontal asymptote was 400. What that means, it says describe what that represents for this company. So what that means is the cost per wheelchair approaches 400 as more wheelchairs are produced. So no matter how many wheelchairs we produce, it's still going to cost us at least at 400 to cover all the costs of whatever goes into the company and then the cost of the chair.